Okay, so this question, you have a pion incoming in a particle detector. It forms a track because it's a charged particle. It's curving because it's in a magnetic field. At this point, it decays and it produces two particles, a muon and an antineutrino. We know that the muon is charged particle and it is confirmed because it produces a track. It continues to curve in the same direction, signifying it's the same charge in the magnetic field. And the antineutrino is not on the track, any of the tracks. It's because it's not charged. However, if this is to scale, we can determine the direction of the collision of the pion just before it decayed. So not collision, direction of momentum just before it decayed. So as the pion comes in, it comes here, it decays at that point. Now, if we look at the direction it was moving just before it decayed, we just draw a tangent to that curve, and we'll see that the direction is almost vertical. So the speed of the pion is almost vertical, and therefore the momentum of the pion is almost vertical. When the mu1 is produced, it starts to curve off in that direction there. Now, the tangent of the curve will reveal the direction of the mu1 just before it moves off, and it's produced, and that's this direction here. So it's produced at this point, and at that point, the tangent to the curve shows that it's moving off in this particular direction. So then you've got the momentum vector for the mu1 on the point of production in this particular direction. This is the angle between the two vectors, and if this diagram is to somewhat scale, then the protractor will measure this angle to be reasonably accurate. I've not got the scale drawings, so therefore you will have to do this yourself. Now, we know that the conservation of momentum applies. A pion is incoming and it decays into a muon and a neutrino. Now, the momentum before should equal to the momentum afterwards. Now, we don't see the neutrino as it's not charged, there's no track, there's no real direction to it. Now, if we rearrange this, we can say that the momentum of the neutrino is the momentum of the pion minus the momentum of the muon. Now, we can do this mathematically, but we haven't been given the vectors in the XYZ direction for the pi or the mu, so therefore we have to do it pictorially. So here we have the first vector. Remember that it's the momentum of the pion minus the momentum of the muon to give you the momentum of the neutrino. Now, the momentum of the pion is in the vertical direction. So this diagram reveals that. Um, the scale that we choose will be relative to the values that are given. So 1.59 times 10 to the minus 19 is the momentum of the muon, and 9.1 times 10 to the minus 20 is the momentum of the pion. So because the powers are different, I've made the powers the same, and we see that it's 15.9 times 10 to the minus 20 for the momentum of the muon, and 9.1 times 10 to the 20 minus 20 for the pion. So I've chosen a scale of 1 centimeter is equal to 1 times 10 to the minus 20 Newton seconds. That means that the mu1 has a momentum equivalent to 15.9 centimeters on my scale drawing, and a pion has 9.1 centimeters on my scale drawing. So when I draw the pion, let's draw that. Let's say that's where we start off. That's easy. It's vertical. So I'm going to start. You're going to draw this a straight arrow up vertically upwards, and that's 9.1 centimeters vertically upwards. Once you've drawn that, we know that the momentum of the pion and minus the momentum of the mu1. So remember, the momentum of the mu1 points in this direction, and we're doing minus that, so we're coming back this way. But nevertheless, we will draw it here. So we start here and we have to end in there, but because we're going negative the momentum, we can draw the arrow pointing this way. And we draw 15.9 centimeters in this direction. Now, What's the angle? It's the same angle between the two vectors. And as we can see, that the momentum of the pion is up here relative to that, and the momentum of the mu1 is up there. And all we've done is that angle there of two lines intersecting is equal to this angle here. So therefore, we can get this vector of the mu1 in the correct direction and the correct size. Now, after we've done that, we know that the momentum of the pion minus the momentum of the muon gives us the momentum of the neutrino, which is, as we start, so we go up into the direction of the momentum of the pion, back against the direction of the muon, and we end up at that point, which is the vector for the momentum of the neutrino. So all we do is draw a line from start to finish, and we will have the momentum of the neutrino. Now this here will reveal the size of the momentum. Using a ruler, the number of centimeters will dictate the momentum using the scale, and then you could find the angle, and the angle relative to the horizontal would be this, or relative to the vertical would be that. So depending on what angle they want, you get your protractor out and measure that angle.